So, how does something just spinning in a circle actually turn into forward speed? It's a cool question, right? It connects going in circles to actually going somewhere. Today, we're going to unlock the math that makes that connection happen. Okay, so picture this. You're on a merry-go-round, kind of close to the center. Your friend is way out on the edge. You both complete a full rotation in the exact same amount of time. But think about it. To do that, your friend had to travel along a much, much bigger circle. So does that mean they're actually moving faster? The answer is a definite yes, and we're about to dig into the math that proves it. To get past just saying, oh, they're faster, and actually figure out how much faster, we need the right tools. Our intuition is great, but physics and engineering need precision. And that precision comes from just a couple of core formulas. And here they are. These two seemingly simple formulas are basically the engine that translates all that circular motion into the straight line speed we actually experience. First up is arc length, which we just call S. The easiest way to think of it is as the crust on a slice of pizza. The formula is beautifully simple. S equals r times theta. R is just the radius of the circle, and theta is the angle of that slice. Now here is the absolute most important part. For this to work, theta must be in radians, not degrees, radians. Our second tool is for linear velocity, or v. This is the speed you'd have if you suddenly flew off that merry-go-round in a straight line. The formula probably looks a little familiar. V equals r times omega. R is still our radius, and omega is the angular velocity. It sounds a bit fancy, but it's just how fast the angle is changing, and you guessed it, we measure it in radians per unit of time. Okay, theory is one thing, but let's actually put these formulas to the test. We're going to walk through a couple of examples right from our source material to see how this all plays out in practice. So this first problem wants the arc length of a circle. We're told it has a 12-centimeter radius and is cut by an angle of pi/3 radians. So we just plug those numbers into our formula. S equals 12 times pi/3. That simplifies down to 4 pi centimeters, which is about 12.57 centimeters. See? Simple as that. And now for what is probably the single most important warning in this entire topic. There's a really common mistake that can completely throw off your calculations if you're not careful. This slide shows that trap perfectly. Look on the left. If you just take an angle like 135 degrees and a radius of 10, and you plug 135 straight into the formula, you get this ridiculous answer of 1350. That's just plain wrong. The correct way, over on the right, requires a critical first step. You must convert 135 degrees into radians, which is 3 pi/4. Only then can you use the formula, which gives you the correct answer of 15 pi/2. And our source material, Baker's math class, really could not be any clearer about this. It's an absolute rule. These formulas are built using the language of radians, not degrees. You just can't mix them. All right, now that we've got the rules down and we know about the big trap to avoid, let's combine everything to solve a real-world speed problem. So here's a scenario. We have a massive monster truck tire, right? It's got a 2.5-foot radius, and it's spinning at 150 RPM, which is just revolutions per minute. The question is, how fast is the truck actually moving forward? The very first thing we have to do is convert RPM into a language our formula can understand, which is angular velocity, or omega. We know that one full revolution is a trip of 2 pi radians, so we just multiply 150 revolutions per minute by 2 pi radians per revolution. The revolutions unit cancels out, which leaves us with an angular velocity of 300 pi radians per minute. Now that we have our angular velocity, we can finally use the linear velocity formula. V equals r times omega. We plug in our 2.5-foot radius and our omega of 300 pi radians per minute. A quick multiplication gives us a velocity of 750 pi feet per minute. And if you crunch that number, it comes out to roughly 2,356 feet per minute. And just like that, we've successfully translated a simple rotation rate, RPM, into a concrete real-world speed. But this math isn't just for monster trucks and carnival rides. It is fundamental to the technology that powers our digital world, especially in how we store data. Think about a CD, a Blu-ray, or an old computer hard drive. All your data is written in these tiny concentric circles called tracks. When that disk spins at a constant speed, say 7,200 RPM, The data on the outer edge is physically moving past the read head much, much faster than the data near the center. It has to cover more ground in the same amount of time. So engineers have to design systems that account for this difference perfectly, all to prevent your data from becoming a corrupted mess. So really, the crucial point, the big takeaway, is this. Whenever you need to build a bridge between the world of spinning and the world of linear distance or speed, you have to think in radians. It's the universal language that makes these connections possible. So now you have the toolkit. I want you to start looking for this relationship out in the world. From a spinning vinyl record to the blades of a wind turbine or even the rotation of the Earth itself. Where else can you spot this hidden mathematical connection between two different kinds of speed? Thanks for watching.